This is a video for EE533 Lab2 demo explanation. Okay, so let's begin. And first, uh, I want to talk about this synchronous AB adder. And you can see I just put the flip-flop after the input pin. Sorry, is before the input pin and after the output pin. And each flip-flop they have enable signal, clock signal, and clear. And now let's look at the simulation. And as you can see, the clear is set to high at the first. So you can see there is nothing from the output. And then you can see after the clear goes down in the second clock, the consequence, um, so we can see the consequence here, 123, which is 92 plus 31. And I want to explain why this 123 is not shown on at the second clock, because this value will be um, will will be shown at the end of the second second clock. So we will see during the third clock. And then I let this saying goes high, and then you can see here 92 plus 32, which is supposed to 124, now it is 125. Also, um, although this seeing signal is sorry goes to high at the fourth clock, but we will see it at the fifth clock. And okay, so this is how this synchronous AB works. And then um, we will go to the 32B ALU, and first we will see the whole schematic. And there are four inputs, which are 32B pin signal, 32B pin A, B, and sub control signal 1B, and 2B select signal. And we have two output, which are 32B result and 1B carry out. And I will explain them separately. First, let's see this add sub 32B, which is a component that can function as addition as well as subtraction. Sorry. Okay. So you can see this is how it works. And I added a 32-bit XOR component into this 32-bit full adder, and there is a subtraction control pin, which means that if you enter 1 and this input B will be inverted, and then we can do subtraction. And also this Cin will be 1, because in binary, when we want to do subtraction, we will do, like, if we want to do A minus B, we will do A plus B in inversion plus 1, right? And if the sub is 0, which means that it just which means that there's no difference from a normal um, full adder, and it will function as an adder. And then let's go to the 32-bit shifter, and it consists of 4 AB shifter, and each AB shifter looks like this, and it's very simple. We just convert the input like A0, and we convert it um, to, like, we shift this input to the left, and you can see the input signal A0 will become the output Q1. Yeah, and the rest of them will all do this shift. And so the LSB of the input, so the LSB of the output will be filled with 0, and the MSB of the input will be discarded. And then we go to the 32-bit marks. And as you can see, it consists of 4 AB marks, and each one I use A421 marks, um, which is very easy to understand. And N32-bit AND gate also consists of 4 8-bit AND gate, and the same as 32-bit OR gate. Okay, so now let's see the simulation waveform of this ALU. So let's Okay, so we can continue now. And as you can see, I set the select signal as 0 first, which means that we are doing addition and subtraction based on this sub signal. And um, so I will convert this to decimal, which will be clear. So save. Okay, so you can see we are doing addition here, and in the and then the sub signal goes up, and we are doing subtraction here. And why this count goes high? Because in subtraction, um, if carry out equals to 0, it means that this subtraction is overflow. And as you can see, there is no overflow here, so it will goes high, so it's normal. And then we can see the shifter. Okay, let me turn it into hexadecimal. And then you can see the select signal is 1, which is 0, 1 in binary. And you can see A is doing logical left shift 1B. So the first 4B F will become E. Um, and then and then and then the ALU will do N. And as you can see, A and B and all the F will become 0. And then we wanna do OR, and you will see because any signal always 1 equals to the signal itself, right? Oh no, um, any signal always 1 equals to 1. So the sequence, the result here is the same as FFFF, right? So this is the schematic version of ALU, and now we will go to the Verilog version to see what's the difference. Oh, sorry. And let's open the project. And yeah, and Lab2, open, Lab2, open. Yes, let's turn off this first. Okay, so now is the Verilog version, and I use uh, behavior um, behavior de behavior design. So it's very simple because we only have one module here and for input to output. Um, you can see I define some variables here and they are used in this always block. And you can see this is the add function and the sub function, and this is shift, this is n, this all, and this is the carry out, and this is raw carry out. Why? Because um, the value of the because the um, value of carry out varies in addition and subtraction, which means that in addition, if count equals to 1, it is overflow. But in subtraction, if count equals to 1, there is no overflow. So we need to do this simple select and then case to select which result to the output. And then we will go to the simulation. Okay, so you can see here first, the same as before. We do uh, we do addition and subtraction first, and I wanted to overflow, so I choose the biggest number of this 30 to be input, and then this count will goes high, and then when the sub signal goes high, it will do subtraction, and this count, since there's no overflow here, as you can see, A is bigger than B, so this count will goes down. Okay, so then shifter, you can see here, you can see okay, so here you can see when the select is 2 is function as n. So here you can see the consequence here, the result here, and the or, and you can see here. Okay, so that's all. Thank you.